I'm going to talk about three topics today that aren't usually clustered together. I'm going to talk about cancer, nanotechnology, and okay, it's going to get a bit technical. So nanotechnology is just about making itsy-bitsy little devices that are cheap. That's it, technical stuff done. And the third topic is diagnostics. So let me start with cancer. So cancer right now on the globe is one of the biggest killers of human beings. I don't mean to keep giving you more depressing statistics, but we'll get to the good stuff later. Cancer incident rates, you would know this as we all get older, are going like this. This is a disease that we need to do something about urgently. So the statistics are such that if we surveyed the people in this audience, if we talked to you, you'd probably found that just about everybody here has been touched by cancer. I have, through my friends, my family, and let me tell you something, it's personal. So my background isn't in biology, it's in chemistry, physics, and mathematics. However, over the past few decades, I've had the sheer privilege of watching absolutely strident advances in our understanding of cancer biology. It's amazing what we now understand of cancer biology. The trouble is that there's this explosion of information in cancer biology, but if you look at the old holy grail that was articulated 50, 60 years ago of what humankind needs to produce, the holy grail was that we'll make one pill, and that one pill will be the magic pill that will be the cure, right? And will make all that cancer go away. So unfortunately, and actually if you look at our medical system over the many decades, it has aligned itself in a model that aligns ever so slightly towards that type of dream. One pill for everybody. So unfortunately, if you look at the advances that we've had in the last decade, we've had very rapid sequencing, cheap, fast DNA sequencing. So, last decade it took $3 billion to sequence a human genome. Forget that. Now we do it for a couple $100 an hour. I can sequence my cat in the time that it takes me to make a cup of tea. Now, that power, which is powered by nanotechnology, by the way, that power allows us to see cancer in ways that mankind has never seen before. And one of the first things that we've seen in the past decade is, in a nutshell, cancer is complicated. And it's more complicated than we thought. And here are some features. The first thing you see, and a lot of people have argued this even before fast sequencing, is that each cancer is different. Every person with cancer has a different cancer. And what's even more frustrating is that if you take a piece of that cancer out of one person, look at all the cells, even the cells inside that lump, they're different. How frustrating is that? And that's really calling a lot of people to say, well, how is that one pill for everyone going to work? It's a bit like asking, we're going to have one tune that will be, excite all the people in the world. And some people are saying that dream of one pill for everyone probably will never happen. We need a new approach. Now I'm sweeping a little bit of stuff under the carpet, but that's the generic. And so in my lab, we've been thinking about this issue from different angles. We've been thinking about this issue of complexity in cancer from where we're from a raw engineering perspective with chemistry, physics, and nanotechnology. What's possible? What could you engineer? And we believe that there is a solution, but it requires realigning that medical system a little bit differently. Well, let me walk you through it. We think that the approach is to really power up diagnostics. That's why it's in my slide. And power it up with nanotechnology to make technologies that mankind has never seen before. I showed you an example a second ago with how cheap it is to sequence genomes. And we feel that if one can power up diagnostics like this, what will happen is each of those individual cancers we'll be able to read individually in detail to know what to do, and it'll be cost effective. And so if you think about, and we think that's the path to truly envisioning a future where we can engineer an end to cancer mortality. And as a physical chemist who works with engineers, I believe it is possible, but we need to realign a little bit and try a different approach. If you think about it, there's really, from that perspective, there's two types of technologies that we need. One is something that I call a scanner. And the other is something I call a monitor. We're going to show you examples of both today. So what's the scanner? The scanner is basically a device. What it will do, you take the cancer and you just bust it open and read all that stuff. And you read whole genome, whole epigenome, whole transcriptome, whole proteome, exosomes, etc. And then you do mathematics to sift through all that mathematical information and find the needles amongst all that hay. And those needles are the treasures. Those needles are the errors that the cancer has produced, and they represent the software that's gone wrong. That's the scanner. Now the thing is, once you've done that once with the cancer, you don't need to keep doing that. You can then use something I call a monitor. Once you have the needles, you can then just look for the needles at trace level, and the cost of the monitor, because you're only looking for the needles, can be effectively invisible. And so we think through this approach, one could, as I mentioned before, engineer big inroads in cancer. And so what I'd like to show you today is examples of those two technologies that we've been developing in our lab and trialing on real cancer patients in the clinic. And some of the results we think are a little bit interesting. To do this, what you need is a unique environment. You need an environment where you have patients, medical oncologists, technology developers, nanotechnologists, mathematicians, engineers, etc. So we've set up a new centre at UQ that has exactly that. And one thing I'm very proud of is that we engage with a lot of patients. And so with the centre over the past 2 years, we've engaged with hundreds and hundreds of patients. So I'd like to start with telling you the story about just one of those patients. So this is actually quite a tragic story. It's patient 205. She was the 205th patient that was engaged through a clinical trial in our centre. It's a tragic story. It's a young 38-year-old woman who's dead. But I hope that part of her legacy, and I'm going to tell you her clinical story, I hope that part of her legacy is to teach us what technologies we need to develop and what parts of that system we need to change to eliminate cancer. Let me tell you the story. So she was diagnosed with acute myeloid leukemia, advanced acute myeloid leukemia. It's a blood cancer. So cancer is complicated, blood cancer is complicated, many different types of blood cancer, but there's one that's really, really bad. That's this one, acute myeloid leukemia, AML for those medicos in the room. And you can see that straight away here in this plot. The reason it's so bad is that it just doesn't respond to anything that we throw at it in the modern conventional medical system. And so what's plotted here is her cancer load. That's the number of cancer cells in her blood over time. And what you can see, and this is very characteristic of the late stage of this disease, is the cells are doubling. These are 4-day increments, so they're doubling every 4 days. Now, the body just can't sustain that concentration of blood cells. So what happens is these patients usually die very rapidly. It's a very aggressive disease. And they die of a stroke or something like that. So for her, palliative care is here. Just to get to this point is amazing. And death is guaranteed around about here. The body just can't sustain it. And the other part of the story, and this is the important part, is before she came into one of our clinical trials, prior to this point, what she had endured was immense. So before here, she had not one, but 2 bone marrow transplants. Now, I won't go to the details of that, but this is an arduous process. The chance of surviving, not 1 but 2, is something like 50 or 60%. So she did extremely well to get that point. After that, she then endured 4 lines of extremely aggressive chemotherapy. And the doctors did, she's young, they did everything they could to try to save her because nothing's responding. They have to try, and that's the best that they have. It's a game of cranking up the toxicity of the chemo to try to get therapeutic effect. And unfortunately, as you can see in the plot, there was a short respite, but then it didn't work. As happens in many of these cases, the cancer has come back. And at this point, all current medical treatment are exhausted, and there's nothing you can do. It's pretty gripping stuff. I mean, this is the things that affect myself and my lab. So she came into one of our clinical trials as a last resort. And what we did is we used the scanner that I mentioned right at the beginning. And it's amazing. I don't sequence the cat, but what we do is sequence cancer cells. And because of these technologies, and I don't have time to describe their details, but they're quite fascinating, the ability to sequence at this speed now, we're able to sequence not just the comprehensive genome of the cancer cell, but we can sequence the epigenome and the transcriptome. For those of you who aren't familiar with this, think of it as a machine. What we're able to do is get a very comprehensive snapshot in hours of the ROM and RAM memory of the cancer machine. It's incredible. I never thought I'd live to see these technologies come to power. They're here now. Now, so when we do this, we can then do something called integrated bioinformatics. And I mentioned mathematics. And this is sort of, it's a bit like a bio-Google. What we can do is we've got all this information. We're looking at, if you like, the hard drive of the cells and what apps the cells are running. We can ask the question, what's wrong with you guys? What programs are you running? Why are you doing this? Why are you amplifying like crazy? That's the first part of the bioinformatics. And that's the searching for those needles I mentioned. So in her case, what we found was really something quite stunning. What we found was that although she has a blood disease, the needle, the driver pathway, if you like, and that's the app that's driving the cancer, the driver pathway really looked like it was a skin cancer. And you might say, a skin cancer? What the hell is a skin cancer doing in a very aggressive blood cancer? Well, welcome to the future of medicine. Cancer doesn't care which part of the body it's in. It cares about the code. The code matters, and now we can read the code. So we looked into it further. And the second part of, I should say with the melanoma, so melanoma, again, it's very complicated, many different types of melanoma. There's one type, a rare type of melanoma that happens at the back of the eye, and it's called retinal melanoma. But, it's treatable. It's treatable. But the driver mechanism of her cancer looked very much like retinal melanoma. What the hey? What the hey? So the second part of the program, what it does is it has a database of all known human drugs that have ever been approved for use in humans and their connection to the pathways. So it runs the search, it's like a biosearch, and tries to connect the driver pathway with the drug. So in her case, all the lights lit up, everything lit up. There's a drug. It sits in a cupboard and it treats retinal melanoma very effectively with low toxicity. It's a tablet. It sits in a cupboard. I think I've repeated sits in the cupboard enough times. It sits in the cupboard. So this gap here is the time that it took, because what we proposed in these few days, it wasn't me, what the oncologist, her medical specialist, proposed was something absolutely outrageous in the current system, the one drug fits all. He proposed that a blood cancer would be treated by a skin cancer drug. So he sought approval of her family, and all the appropriate places to, at this point, on her last legs, administer this. It's a tablet, a relatively safe tablet. And this is what happened. So the tablet was administered here, and what you can see is that it took effect immediately. Nothing else worked. Chemo didn't work, bone marrow transplant didn't work. The tablet worked immediately, and then within 3 days, the cancer dropped down to almost zero. She technically went into remission. And I have to tell you, when I saw this result, I still get a bit emotional when I talk about it. I just fell off my chair. I couldn't believe it. Now, and the other thing is I'll often say it, but if this was such a spectacular result, first I didn't believe it, then we checked it. And if there's nothing else that I do in my career, this is enough. But we've got bigger plans. We followed her bloods right along. I should point out that at this point, she was so depleted from the chemotherapy and all those treatment that she needed to recover from all of the other treatments that hadn't worked, but then eventually was released from hospital to her family. And I've got pictures of her riding a horse. There's some very cherished photos. We've tracked the blood. The cancer did actually keep going back to zero. One of the frustrating things here too is that this is now, it's a genetically confined system, and so sometimes these cancers mutate back, but there's now a second and third tier drug, if it ever did. But then 4 months later, she died. What did she die of? She died of a heart attack. So you can ask yourself the question, why would a 38-year-old woman, young woman, die of a heart attack? What did she have back here? She had a load of chemotherapy. What happens to 60%, I think it's like 40 to 60% of aggressive chemotherapy patients for AML? I'm not poo-pooing chemotherapy, but in this one case, round about that fraction die of these drugs are very cardiotoxic. They poison the heart. And so she died of a heart attack induced by the chemotherapy. It's a side effect. The doctors did exactly the right thing. It's just that they have no other options. It's the one drug fits all model. It's a tragic story. But then what can we learn from this? Well, I think there are some powerful lessons here. One, in terms of the technologies we need to develop, and two, in terms of how do we need to change the system to make a bigger impact in cancer. Let me hit those two things. So first, we need to have early screening. It just stands out like crazy. Imagine if I could have sat down with her whole medical team and the data. It would have been here at this point, even before she had the bone marrow transplant. We could have had a conversation. It's like a scene from The Matrix. Do you want to take the red pill or the green pill? You can try the pill. Did I mention it was in a cupboard and it's low toxicity? Or you can go and we can try that out for 2 weeks and see if it has an effect. If it doesn't, then there's the chemo, there's the bone marrow transplant and chemo, no problem. I wonder which choice she would have taken. Actually, I know which choice she would have taken. The next thing is we need, so this is the scanner. We need the personalised treatment. This is the monitor. And the other place where we need the monitor is here. And now monitoring in our modern system, we don't do that very much. It sounds crazy from an engineering perspective, but we just don't. People get chemotherapy and basically they just kind of go home. They get, scans and you have a consultation. But we should be monitoring the disease to see if the therapy has worked. If it hasn't, flip the treatment. And if the cancer's come back, get in there early before it can do some other damage. Now, our lab now focuses very much on, I've mentioned the scanner and the monitor technology. So for what remaining time I have, I'm going to show you examples of the monitor technologies. And so for the monitor, as I mentioned earlier, we need nanotechnologies to make these, if you're going to go into a screening or a monitoring program, to make these very cheap and very accurate. But let's first look at how it's currently done in the current system. So this is how pathology is done today. It's very typical. By the way, it really strikes me as a sort of a chemist, nanotechnologist, that it's quite interesting that in our system, although cancer is a disease of the DNA, we don't commonly look at the DNA of those patients. We do through histopathology, etc., but it's not comprehensive. That's something that needs to change. But if the DNA is analysed, and I should just point out, this is palaver. What happens is somebody takes a sample and zap. Palaver is an Australo-Yiddish word which means a lot of bother. So there's a lot of bother. We get a sample, off it goes to a lab, and then maybe the information gets back to the doctor and he does something, hopefully. But it's very expensive, lots of technicians, lots of dollars. This soaks up about 20% of our current healthcare budget, and it's increasing like this. We need new technologies to drive the cost of this down. Very much so. Now, for DNA analysis, when it's done, there are 3 key steps, and I need to point these out. One is the DNA extraction, to pull out the DNA from blood or tissue or whatever. Next is the DNA amplification, and each of these takes a bench, one of these things, a bench, and a technician. So the application with PCR, something like that. And then the third step is what's called the detection. And for that, we'd need another bench and a person. It'll be synthesis by sequencing or a fluorescence readout, RT-PCR, things like that. And that's how it's done. So what we've done in our lab is we've miniaturized all 3 of those steps. We've used nanotechnology to miniaturize each of those 3 steps into one droplet of fluid, so that you can do the test yourself. You don't need a laboratory. We've effectively miniaturized that whole lab into one drop of fluid. So it's all described in this paper. This is the extraction step where you get a single strand of DNA, if you like. The megaphone is a schematic which shows how that molecule is amplified automatically. So the drop contains all the molecular machinery and nanoparticles to do this automatically. It's programmed. And then the nanoparticles that are in here are programmed, so if that amplification reaction happens, they become like Velcro basically, they precipitate and you see it by eye. The key features of the test are that what you have is comprehensive DNA and RNA analysis within a single drop, as I've mentioned. Now, unlike the lab, there's now no lab required. There's no training, no personnel. Even I can run this. And it takes 45 minutes to run. You can do this yourself. It's similar to a pool test, for those of you who have a pool. I mean, I do this all the time. You take the sample, you do a bit of this, and then you look for a colour change. That's it. But now this test isn't looking for pH or chlorine. It has single DNA molecule sensitivity. We think that's pretty cool, because that's trace. That can look for those needles that I mentioned. We've adapted this for all pathogens. We've shown that it works for HIV, tuberculosis, cancer markers, obviously, and saliva, blood, urine, all have been published. And cattle herpes. I don't know why cattle get herpes, but I don't know why they get herpes, but if they get it, we can test for it, and it's in this paper, and please go ahead and read about it. But also, another interesting fact is we can do multiple tests at once inside the droplet. So it's a DNA scanner. Basically, you program it to look for, at the moment, up to 3, and in the future, many more. So we think it's ideal as a monitor and ideal for point of care. I'll just contrast this with the $3 billion comment I made on the introduction. You know, this obviously doesn't do whole genome sequencing, but it doesn't require the $1 million pieces of equipment that we used about a decade ago. That's something to keep in mind. Here's a video of how it works. I'll just show you quickly. You do a bit of this, put it down, and then with 13 seconds, the nanoparticles give you the answer. That's a yes, that's a no. That's all there is to it. And as I mentioned, these are individually programmable. We've extended this now for any tech heads out there for DNA, RNA, and epigenetic signatures. So if you remember with 205, we looked at DNA, RNA, and epigenetics. In this, we can do this here as well. And we think that's rather powerful. Now, in whatever time is left, I want to show you just one last monitor, because this isn't just applicable. This concept is applicable not just to leukemia. It's applicable for all cancers. So for all cancers, this is our picture of how cancers spread. We think that what happens, it starts with one cell that goes a bit haywire, and then it forms a primary tumour. Now, this guy is threatening, but he's safe. If we can detect that early, for example, in breast cancer, early detection is almost as good as a cure. It gives rise to almost 98% survival for patients with some surgery, a little bit of therapy. The problem, the really big problem in cancer is this blue guy. What happens is they break off and then they travel in very small numbers, like criminals in a city, through the bloodstream. So, and they will then form, little gangs, I had to use this analogy, which are secondary metastatic sites. And they are the really dangerous agents. They kill. Now, the problem is that in the hospital systems, we have no eyes at all on this system. The oncologist doesn't see it. He doesn't know if it's happening. He has to treat the patient as well as he or she can. So one of the holy grails here is to get some eyes on this. Again, it's a needle in a haystack game. For a metastatic patient, typically one would have 50 cells in a ml of blood, which would have 10 million healthy cells. So it's the criminal in the city. 50 cells, 50 bad guys for 10 million good guys. How do you find them? So here's how we do it. We use nanotechnology. So in the video, you'll see that this is blood moving, and the reason the blood moves is we attach we attach little alligator clips that supply an AC voltage. It's 0.1 volts, 1 kilohertz. When the voltage is applied, the AC voltage is applied, the blood moves. When you stop it, it stops. For the physicists in the audience, I'm sure there are some somewhere, this is not capillary phoresis, it's an electrohydrodynamic phenomenon. I don't have time to go through the details, but all you need is a relatively cheap chip and a 0.1 volt, 1 kilohertz signal, which can be supplied by an iPhone. That allows you, and that's the sort of, there are other technologies now that are coming on the market, but the feature of this is its accuracy and its cheapness. Now, I don't have time to go through the physics. The physics, I'm biased, I think is quite exquisite. It drives fluid flow within nanometers of the solution. And I'll skip it for the interest of time and just show you a movie. But we've published all of this stuff if anybody's interested. If you have a look at the chip, what there are is thousands of these asymmetric pixels. There's the AC voltage. The red guys are the bad guys that we're trying to catch. And the way it works like a microscopic airport security station where all the cells are patted down, the good guys are let through, and the bad guys are held on. The cool thing is that if we take a cancer patient with 100 cancer cells, this chip will find 90% of those cells accurately each and every time. And we think that's a little bit cool. And we published that in all of these publications. The other one, so this starts to give you eyes on that process. The other wonderful thing about this is that once you catch the robbers, you can interrogate the robbers. So we know they're there. We can release them, bust them open, and then we bring in our scanner. And we look at their genome, epigenome, transcriptome, and ask the question, what's wrong with you guys and why aren't you dying when we give you a bunch of drugs? So this, again, is it's just a second example of a monitoring technology and how these things are becoming cheap and I think in the future invisible. So I want to finish where I started. I want to finish with patient 205. What are the lessons from patient 205? And I hope this will be one of her legacies. One of her great legacies is that she teaches us what to do. And I think the first one is we need to change conventional cancer treatment. It stands out so clearly. If you look at her case, she's what's technically called an exceptional responder. But it's the exceptional responders that are the jewels in the clinic. They teach you everything. We need to embrace the fact that each cancer is different. And we need to analyze it at a molecular level, read it at a molecular level. We need to embrace new technologies to detect early, personalize and monitor. It's so clear. And most importantly, we need to translate these powerful new nanotechnologies from the lab into the clinic. We need to shift that old medical system just that little bit into a new paradigm. I've got one last slide and I'm going to finish there. So in the work that we do, it's very unusual that we would ever meet or even learn who the patient is for a sample that we analyze. And that's as it should be. It protects the privacy of those individuals. What we get is de-identified samples. So by a process of serendipity, not long ago, my lab and I had an opportunity to meet the family of patient 205. Let me tell you, it was a very humbling experience. And I had the honor of learning a little bit about her life and about her dreams. And I want to finish by sharing with you a little about her and one of her dreams. So this is patient 205, Alexandra Coxley Rowe. She was loved dearly by her family and friends and known as Alex. She was, as you would imagine, someone of absolutely tenacious courage. That is what I hear. That tenacious courage was tinged with a biting humor and, from what I hear, deep wisdom. She was very grateful of the radical approach that was trialled to reverse her refractory cancer and knock it down to zero. And she had one wish that I think we should remember. Her wish, her vision, if you like, was that that treatment that she received would one day be a frontline treatment, early, not a last resort treatment. That's a vision that really motivates me and my lab, and I think it should behoove all of us to make that happen and make a difference. Thank you.